Hello class, this is the video for section 4.2, talks about the mean value theorem. In this video, at the end, you should be able to understand and interpret what the mean value theorem is. We call it MVT, and apply this to situations. Okay. But before we talk about the mean value theorem, there is a theorem that precedes that we need to know, but they are related. Okay, so we see that many of the results that we have said in this class depend on one central fact, which is what we call the mean value theorem. But to arrive at this very theorem, we first need to the following result. We call the Rolle's theorem. Okay, say that let f be a function and satisfy the following three conditions or hypotheses. Okay, now f is continuous on the closed interval, and it is differentiable on an open interval. And then the function values at the endpoints of the points are equal. Now, if that is the case, the conclusion is that there is a c in the open interval such that the first derivative differentiated and evaluated as c, it is equal to what? Is equal to 0. Okay. Now note that this c that we are talking about may be what critical number from what Fermat's theorem. Okay. Now, now notice that we said that a function could be what? If it is differentiable, it is what? Continuous. But if it is continuous, it's not necessarily what? Differentiable. Okay, that's it. One of the theorems that we studied a while back. Now, the following graphs, okay, depicts the hypothesis of what? This Rolle's theorem. And these are the figures A, B to D. Now, notice that at C, okay, now what's the function value of P? This function is continuous, a constant function is continuous, it is differentiable, and the function value at B and then A are equal. That is, this is where the Y value is. And then if you go to B, the same thing, okay? So it means that there is a C1 or the C2 within the interval AB such that the F prime, okay, F prime of what? C is equal to what? 0. F prime of C equal to 0. And then for B2, same thing happens. Now, this is the function value, okay? FA, FB are the same. The function is continuous on this interval and is differentiable where the tangent line, I could see that here, F prime is equal to 0. Here to the same thing, F prime equal to 0 for this side, F prime is equal to 0. And here, F prime is equal to what? 0. And then at each point, the function values are equal. So we say that if these three, it is continuous and differentiable, and then the function values at the endpoints are equal, then there is a C in the open interval A, B, such that the word F prime of C is equal to 1. Where C is what? Is in that interval. It's a member of. Okay, this is a what? Member. All right, so now let's take some examples. So it means that in each of these cases, it appears that there is at least one point, okay, on the graph where the tangent line is what? Is horizontal. So that's the Rolle's theorem is what? Is plausible. Okay. Now, exercise number 5. It said verify that the function, okay, which is given, satisfy the three hypotheses of the Rolle's theorem, all right? And then on the given interval, which in this case, -1, 3. And then find all such numbers, C, such that it's what the conclusion of what? Of the theorem. All right, so the solution here is that I, is that the function is what? It is continuous. Now F is what? Is polynomial. F is polynomial and what? Continuous on the what? On its interval, which is what? From -infinity to what? Positive infinity on all real numbers. Okay. So if it is continuous on that, then it means that F is what? is continuous on that this interval, which is -1 and 3. Okay. Then the second part of the theorem, that is 1, this is 1, and the 2, it said that it is differentiable. If it's polynomial, so f is what? Differentiable. F is differentiable, sorry, on the open interval, what? -1 and then what? Then the third part, okay, says that f of what? F of A equals what? F of B. So we want to verify this. What is f of -1? If you substitute this into that, so you have for 2 minus 1 squared minus 4 times minus 1 plus 5. This is equal to 11. And what is f of what? 3? That will give us what? 2 times 3 squared minus 4 times 3 plus what? Plus 5 is also 11. So we see that f of what? -1 is equal to f of 3. So if that's the case, then the conclusion, all right, the conclusion of the theorem, there is what? There's a c which is in the interval -1 and 3 such that, okay, such that f prime at what? At c is equal to 0. So first, what is f prime of x? This will give us what? 4x minus 4. Okay, so then let's see what is f prime at c. This is what? 4c minus what? 4c minus 4. Okay, now you set this to 0. That means that we have 4c minus 4 equal to 0. So c is equal to what? 4 over 4, which is what? So we see that c equal to 1 satisfies what? The conclusion. The conclusion of what? Of the Rawls what? Theorem. The Rawls theorem. Okay. So you see that first the hypothesis 1, 2, and then 3, and then therefore the conclusion. All right. Now here is another example. Same thing, we repeat for exercise number 7. Okay. So it says that satisfy the 3 hypotheses the same as we did before, and Rawls theorem, we want to satisfy the conclusion of that. Okay. So just like we did. Now, as you can see, the hypothesis, the first one is that it is continuous on what? On that interval. Okay. So what is S? S since what? F is what? A sine function. Since it's a sine function, it is what? It is continuous. It is continuous on what? All real numbers. It's a sine function. And so, continuous on the interval given. Continuous on this interval, which is what? Pi by 2 and 3 pi by 4. Then, sine function is differentiable. So we say that can also say that since f is continuous on that, it is differentiable. Okay, since f is continuous on the array numbers, okay, it is differentiable. It is differentiable on the whole set of all the numbers, and hence it is what differentiable on the given. Pi by 2 and 3 pi by what? By 2. Okay. So the third one, number 3, says that f of what? F of A is equal to f of B. Okay. So we want to find what is f of pi by 2. F of pi by 2 is what? Sine f of what do you call it? F of 3 is what? Sine pi by 2 times 1/2, which is equal to sine pi by 4. And sine pi by 4 is actually what? Root 2 over 2. And then also, what is f of 3 pi by 2 will give me sine x over 2. So that is what? Sine 3 pi over 2 times 1 over what? 2, which is sine, what do you call it? 3 pi by what? 4. And this is the second quadrant, so it's also positive. Okay, it's in the second quadrant. Okay, so then what is the conclusion? The conclusion is that there is what? F prime at C is equal to what? There is a C in the interval, pi by 2, 3 pi by 2, such that this is true. So if we differentiate sine, okay, when we differentiate that sine, okay, we differentiate sine, you have what is f prime of x. Let's do that. This will give me cosine of what? X over 2 all divided by 2, which is what? 1/2 cosine of what? X over 2. Okay, so what is f prime at C? That'll give me 1/2 cosine of C over what? 2 is equal to 0. We set that to 0. And if you multiply through by 0, you have what? So you're going to have what? C over 2 is equal to what? The cosine inverse of what? Of 0. The cosine inverse of 0 will give us what? Which will give us pi by 2, and then what? 3 or 3 pi by what? By 2. So either is a pi by 2 or 3 pi by 2. It's in that interval. Okay, so therefore, what is what? What is C? C is equal to either 2 times pi by what? 2, or 2 times 3 pi by what? 2. And this cancels out. Okay, this is what? Pi. And that gives me or 3 pi. Now this 3 pi is outside. Okay, you see that this is not in that interval. It's not a number of what? It's not in the interval 5 2. So pi by 2 and 3 pi by what? By 2 is outside. So the only C value is this one. Okay, that's the only C value. All right. Now let's go to the main theorem, the mean value theorem. So our main use of this theorem is improving the following what important theorem, which was first stated by another French mathematician, Joseph Louis Lagrange. Those who are doing engineering, you're going to see Lagrange a lot in physics and then in engineering. So you look out for this guy. He's done a lot of things. Now, here is the mean value theorem. Okay. Now it says that if f is a function and satisfy these two conditions, all right. The first one is that it is continuous on the closed interval, and it is what differentiable on the open interval. Okay. Now, then this is true that there is a C in that open interval such that f prime of C is equal to f of B minus f of A divided by. Now, notice that, okay, the right hand side here is what? Is the average what? Is the average velocity. Okay? Is the average. If you is the average rate of change. Let's put it that way. Because that's the rate of change. So what does it mean? Now, of course, if you divide this by 2, 1 and cross multiply, you get the second one. Okay, that is f of b minus f of a equals to the f prime at c times 1. Okay, so this is the same. The 1 and 2 is the same. They are equivalent. All right. So what does this mean in practical sense? Right? The mean value states that at some interval, remember the rate of change is the average, the velocity at what? Any point over the journey. Okay, that's the rate of change. So the mean value theorem basically says that the instantaneous, okay, change f prime in a certain point in that interval, the average what rate of change is equal to the instantaneous rate of change. Okay, for example, if a car is accelerating from 0, takes 8 seconds to go 352 feet, its average velocity is what? 44 feet per second, because if you divide 352 by 8, you get this. Now, the mean value theorem states that at some point during the acceleration of the car, the speedometer must read exactly what? 30 miles per hour, which is the same as saying that 40 miles per hour. 40 feet per second, not times. This is per second. All right. So that is the physical interpretation of what? The mean value theory. Now let us apply it. Okay. Let's apply this to real life situations here. Okay. Now, so again, we want to verify the hypothesis of the theorem, and then find C that satisfies what? A's conclusion. Okay. So let us look at it. Similar to the Ross theorem that we talked about. Okay. Now, so what is the hypothesis? Okay. The first one, it says that it is continuous on what? A's interval. Now, F, we know that F is what? Is continuous. It's a polynomial. Okay. F is a polynomial. And continuous on the interval, all real numbers. Therefore, or hence, continuous on what? On the interval given, -2 to 2. Okay. Now, 2, since it's continuous, okay, since f is what? Continuous, it is differentiable. It is differentiable on R, on this domain, which is -infinity to infinity, and hence differentiable on that interval. So it's an open interval, -2 to 2. Now notice that when you say continuous, it's what? It's over the closed interval, okay, the interval given, and then when it's differentiable, it's what? Over the open interval. So if this is the case, then what we are saying that the conclusion is that the f prime at C is equal to what? F of what? B minus f of A divided by what? B minus A. Okay. So in the first, let's differentiate this. What is f prime of x? F prime of x is what? 3x squared minus 3. And so f prime at C, we substitute what? C for x, that will be 3c squared minus 3. Okay, now what is f of a? F of a is my a is what, -2. So that is f of -2. This is going to be what, 0. And then what is f of what, b, which is the f of 2, which is giving 4. So what we're saying is that the conclusion says that the f prime at a certain c is equal to what, f of b minus f of a divided by what, b minus a. Now this is 3c squared minus 3 is equal to 4 minus 0 over 2 minus 2, which will give us 4 over 4, which is equal to 1. So that means that we have 3c squared minus 3 is equal to 1. Okay? And then that gives us what? 3c squared is equal to 4, and then c squared is equal to 4 over 3. So that implies that c is equal to the plus or minus, okay, the square root of what? 4 over 3, which will give us the plus or minus 2 with what? 3 over what? Over 3. Okay. 2 root 3 over 3 is in that interval given. Okay. Right? If you have 2 root 3, let's see the value of that, which is 2 root 3, okay, divided by 3 is 1 point. So we have 1.15, so plus or minus 1 point, which is within the interval. So these are the values of what? Of C that satisfy the what? The conclusion of the mean value. Okay, let's take another example. Okay, here's a natural log. Okay, so we say that what's the domain of a natural log? Okay, the first, okay, what's the domain? F is natural log of x, okay, which is what? Which is continuous. It's continuous on its domain, which is what? 0 to what? Positive infinity. Okay. Therefore, it is continuous and what? So continuous on that interval given, which is 1, 4. Okay. Then 2, f is differentiable. I'll just say that f is what? Differentiable on the open interval 1 and 4. So then we can conclude, if that's the case, then we can say that the f prime, there is a c, okay, c in what? The open interval 1, 4, such that the f prime at c is equal to what? F of b minus f of a divided by b minus a. Okay, so first let's find the derivative of the function. It is natural log, so that gives me 1 over what? 1 over x. Okay, so f prime at c, that c we are talking about is 1 over our c. That is, we substitute c for x. So then let's find the what? What is f of a? In this case, will be f of function value at what? At 1, which is what? Natural log of 1, and that gives me 0. And then what is b is what? F of 4, and that gives me natural log of 4. Natural log of 4. Okay, natural log of 4. Therefore, if you have if you want to find the what? The function, okay, so you have f of prime at c is equal to the f of b minus f of a divided by b minus a would then be what? The 1 over c is equal to natural log of 4 minus 0 over what? 4 minus 1. and that gives me natural log of 4 over 3. So that means that if you find, then C, if you flip that will be 3 over what? Natural log of what? Natural log of 4. So then this will be the one's answer, the C value, such that the conclusion of the mean value theorem is what is satisfied. Okay, so then here's another example. There's 2 more, and then we're done with the section. It says, suppose that f of 0 is equal to negative 3, and then f prime of c is less than or equal to f for all values of x. How large can f of 2 possibly be? Okay, so the solution here, we are given that f is differentiable. That is why we can find the derivative, and therefore it is continuous. So the function is differentiable, then it is what? Continuous at any point over the interval. But remember, if it is continuous, does not necessarily mean it is what? Differentiable. Okay, everywhere. In particular, we can apply the MVT on the closed interval 0 and 2. Okay, because we have f of what? Since we have found f of 0 and f of 4, 2. So this is my f of b, and that is my f of 4, f of a. That's why it's between 0 and 2. So it means that according to this, the mean value theorem, so f prime at c is equal to f of 4 b minus f of 4 a over what? B minus a. So for we have for f of b minus f of a is equal to f prime at c times what? B minus a. And that's what we have done here. My a is 0, my b is what? Is 2. Okay. So if this is the case, then we know that f of 2 in this case will be equal to what? F of 0, then plus what? F prime at c times what? 2 minus 0, which will give us what? F of 0 plus 2 times f prime at what? C. Okay, so then what next? How do we determine the maximum value of that? Okay. So this is what we just did. If you substitute that into that, then f of 2 is equal to negative 3, because the question says f of 0 is negative 3. So we are given that this is given is less than or equal to what? It's equal to 5 for all x. So in particular, we know that f of c, okay, f prime of c is less than or equal to 5. So, but if you multiply this by this inequality by 2, you have for 2 prime of c less than or equal to 2 times 5, which will give me less than or equal to 10. So 2 prime at c is less than or equal to 10. So that means that the f of 2, okay, which is minus 3 plus 2 f prime at c will be less than or equal to negative 3 plus the 10 that we have, which in this case is equal to 7. Therefore, the largest possible value of f of 2 must be what? 7. Okay. Now, here is a corollary, okay, a corollary of the theorem that we talked about, in terms of what? Constant functions. So the mean value theorem can be used to establish some of the basic facts of differential calculus. Yeah. Of these basic, these are the 2. So theorem number 5 says that if f prime of x is equal to 0, that means that that's a critical number for all x in that interval less, then f is what? Is constant. F is constant over that interval. And then the corollary says that if the f prime of x is equal to f g prime of x for all x in the same interval in b, then f minus g is also constant on that interval. That is, f of x is equal to g of x plus c, where c is what? Is a constant. So that when you find f of x minus g of x, which is equal to the constant, in this case, which we'll say that which is what? That's what we have there. All right, so here's an example. Let's consider a function f of x given by x divided by absolute value of x. Now, we know the absolute value of x is either what? It is either x when x is what? Greater than or equal to 0, and minus x when x is what? Less than 0. So the denominator here, we have x over absolute value of x is equal to x over x if x is what? Greater than or equal to 0. Okay, and that will give me 1. And then the second part is that this absolute value of x is equal to x over negative x, which will be negative 1 if x is less than what is negative. So that's why we have what? This piecewise function. Okay. Now, what's the domain of this? The domain is what? In fact, everything except what? X is not equal to 0. All right. So f, the prime of x, if you differentiate f of x, because constant is equal to 0 for all x in that interval. But f is obviously not a constant function. This is what do you call it? A piecewise function. It's not constant. This does not contradict the theorem because the domain that's given is not an interval. It's just not equal to, it's not an interval. Okay. Notice that f is constant for the interval of 0 to infinity or negative infinity to 0. Because that's why it's positive and it's less than. Okay. So you have that function. It's going to be the graph of that. We're going to look like this. It is positive 1. Okay. And then it's negative 1 going this way. Where you have 4, it doesn't go this. And that is your x. So, okay, so that brings us to the end of this section. All right, see you next time.